Bismillahirrahmanirrahim. Hello and welcome to Rahman Digital Production. This is lecture number 96 of physics, and today we are going to start a new topic with the name sound. One major reason for learning about sound is that we experience it every moment of our lives in the form of music, noise, and communication. From the large vocabulary we have of sound, for example, clank, ping, bang, pop, hiss, and the different adjectives that we have to describe sound, for example, high, low, soft, loud, mellow, pleasant, sharp. We certainly have a great variety of sounds. We will be learning how sound is produced, how sound can be classified, how sound travels through various media, and other topics. The more we understand about the sound, the better we can use the and control it. Now, in this regard, the first topic we have to understand is the nature and production of sound. So let us first discuss it, that what is the nature of sound. Sound is a form of energy that is passed from one point to another as a wave. Remember, dear learner, that heat is a form of energy, wave is a form of energy, light is a form of energy. Similarly, sound is also a form of energy. As mentioned in the previous unit, sound is an example of a longitudinal wave. Sound is produced by vibrating sources placed in a medium. Yes, you have to understand that medium is required for the propagation of sound waves, which are longitudinal in nature. The medium is usually air, but it can be any gas, liquid, or solid. A vibrating object in a medium such as air produces sound waves through the shifting of layers of air particles. This is similar to the longitudinal waves produced when a slinky spring is vibrated parallel to its length. Now you can see two figures, and those two figures show two common example of vibrating sources that send out sound waves into air. Now the nutshell of this is that sound is a form of energy that is passed from one point to another as a wave. So let us talk about these picture, and one of the most important one is the tuning fork. A common vibrating source of sound is the tuning fork. A tuning fork is an instrument with two hot steel prongs. Now, ladies and gentlemen, these are called prongs. This is prong. Let me make it red so you will see. These are the prongs, and this is the rubber pad. When we want to produce sound, we have to strike this tuning fork's prongs with the rubber pad, and then sound will be produced, and you can hear that sound very clearly. It produces a musical note when you hit it. Figure shows the longitudinal nature of sound waves produced by a vibrating tuning fork, which you can see here that it is longitudinal in nature. In this picture you can see Now, note that a series of compressions and rarefactions are produced by the shifting air layers. How it is produced? So, it is in this case, it is in normal position. It is in normal position when there is no disturbance of the air particle. When we strike the prong of the tuning fork with the rubber pad, and then the prong will move to and fro like this. And when it is moving in this way, then it means that it will compress the surrounding air's particles, just you can see, and the density at that point will be higher. And this portion is not yet been compressed by the prong. So this compression is transfer further, as you can see in this area, and this part will become a rarefaction in this way. So in this way, the sound waves which are longitudinal in nature are transmitting from one place to another place. Now, ladies and gentlemen, let us talk about the transmission of sound in real. Now, these are the air particles you can see in the form of dots. In one place, the density of air particle is high, while in this case, you can see the air density is not that much higher as to the surroundings. The location or the place or the places where air pressure is slightly higher than the surrounding air pressure is called compression. So this area is compression, this is compression, this is compression, this is compression, and this is compression, which we are denoting by C. And the second definition is rarefactions. Rarefactions are places where air pressure is slightly lower than the surrounding pressure, as you can see in this particular area. This is a rarefaction. This is also a rarefaction. This is also, and similarly, these all are rarefaction. So the prong, when moving towards the right, they are compressing the surrounding particles and making it as denser one, and that denser location is known as compression. When this compression is transmitted to the nearer layer, that compression by itself becomes rarefaction, and they are pressing the nearby air particles, making them as the compression then. So in this way, compression and rarefaction are transmitted forward. Now, very important thing here we have to note that sound wave is an example of a longitudinal wave. Sound wave is an example of longitudinal waves. For sound waves in air, compression and rarefaction can be thought of as changes in air pressure. Compressions are places where air pressure is slightly higher than the surrounding air pressure, while rarefactions are places where air pressure is slightly lower than the surrounding air pressure. Now, the figure which we will observe right now shows the sound waves produced in a hollow pipe of air by a vibrating diaphragm of a loudspeaker. Now you can see that there are areas which is having low density as I am encircling them, and there are area which are looking more denser than its surrounding. So in this way these area are represented by rarefaction, and this is compression, and this is rarefaction, this is compression, this is rarefaction, and similarly alternatively we can see that there are rarefaction and compression. If we are taking it in the form of a sinusoidal waves, then there will be rarefaction which will be at the bottom. This is compression, this is then rarefaction which is called crust, and this is then compression which is passing through the crust. This is trough, this one, and that is the crust. So in this way if we want to find the wavelength, then this will be the wavelength of the longitudinal waves in this case, because we understand from the definition of wavelength that the consecutive, the distance between two consecutive trough or crust is known as wavelength. Now this area is known as rarefaction. This area is known as rarefaction, while this area is known as compression. This is compression if we are talking about and comparing the longitudinal and transverse waves. So that is the wavelength. Now this will be the amplitude. If we are taking this area, so this will be the amplitude. And similarly, this area will also be an amplitude. So we are having in this regard the distance between two consecutive rarefaction and two consecutive compression. In this case, if I am talking, then this will be the wavelength. Similarly, this will also be the wavelength, because the distance between two consecutive rarefaction and compressions are known as what? They are called the wavelength. So this is the high air pressure here, and this is the lower air pressure. So that will be low and this will be high air pressure. So these are called the rarefaction, and that is the, you have to consider that this is a hollow pipe. Let me denote it by blue line. So that is a hollow pipe in which these air particles are producing disturbance, and as a result they are producing what? Rarefaction and compression. So at any one place along the pipe where the sound waves travel, the air pressure rises above the surrounding air pressure and then drops below the surrounding air pressure. This rising and dropping of air pressure takes place continuously and regularly as long as sound is produced. The distance between two consecutive compressions or rarefaction is the wavelength of the sound wave. The maximum pressure changes gives the amplitude A of the sound waves. Keep this in mind. Now let us turn our focus to the mechanical nature of sound. How sound is transmitted. Is it mechanical in nature or not? What does it mean? It means that sound waves need a medium for its propagation or not. We learn in the case of electromagnetic waves that they requires the medium. Without medium, no medium is required in case of electromagnetic waves. Now, to study the nature of sound, we are going to perform a very famous bell jar experiment. There is a jar you can see in which there is electric bell there. There is wiring system for this electric bell, and these are called wires, these are called threads, this is cork, and this is bell jar. There is air inside that. So sound waves are mechanical in nature in that they require a medium through which to move. Unlike light waves, which are electromagnetic in nature, sound waves cannot pass through a vacuum. The bell jar experiment can be used to demonstrate that sound waves cannot pass through a vacuum. Before starting the pump, which is used to remove air from the jar, this is the pipe and this is the vacuum pump. Before removing before starting the pump, switch on the electric bell. You can see the movement of the striker and hear the sound at the same time. You will see that this gong is struck by this hammer. So at the same time you will see that the hammer is moving and hitting the gong, and at the same time you will hear the sound as well. So when the vacuum pump starts, the sound becomes fainter and fainter with time. Finally, it becomes so soft that you cannot hear it anymore, although the striker can still be seen hitting the gong. If you let the air back into the bell jar, sound is heard again. What does it show? This shows that without a medium, in this case air, sound cannot be transmitted. What is the nutshell of this experiment? In this experiment, care must be taken. Yes, one care must be taken that this hammer is not touching the body of the jar, that the bell should not touch the glass, and the connecting wires used must be thin. Yes, the wire must be thin. This is to prevent any sound waves from being transmitted through them to the outside of the jar as the striker vibrates vigorously. So this famous experiment, bell jar experiment, is confirming that sound waves are mechanical in nature. It means that it requires a medium for the propagation of these types of waves. Our next observation is the medium of transmission. It means that from which medium sound can pass, whether it can pass through the gases, solid, or liquid. So let us discuss that the medium of transmission. Remember, dear learners, any medium which has particles that can vibrate will transmit sound. But the nature of the medium will affect the speed of the sound waves. In case of gases, the speed will be 1. In case of solids, the speed will be another one. And similarly, in case of liquid. In general, the speed of sound in a liquid is 5 times that in gases. So it means that the speed of sound is 5 times greater than in the gases. And another thing, the speed of sound in a solid is about 15 times that in the gases. What does it mean? It means that sound travel fastest in solids. As I have written it here, that sound travels fastest in the solid. The table shows that in air, the approximate speed of sound is 300 meter per second, while in water that speed becomes 1500 meter per second. So it means that 3 5s are 15, so it is 5 times faster. Now in this there is 1500 and 5000 in iron, which is a solid. So it means that it is 15 times greater than the water. So in this regard, we can conclude that sound travel fastest in the solids. This explains why in older days, when wars were fought using chariots, an army of approaching chariots could be detected by placing the ear against the ground even before hearing them in the air. Table which is given to you shows typically speed of sound in different media. This table. Now, is there any factor which is affected the changes in some physical condition? Yes. The speed of sound in air is affected by changes in some physical condition. The table shows the effect of physical conditions on the speed of sound in air. Now the first term is temperature. The speed of sound is proportional to under the root T. T means temperature. So yes, if the temperature is high, then it means the particle will move from each other apart and they will not be able to transmit the sound very quickly. On another hand, if there is a less temperature, it means that the density of air particle, there will be humidity in the air that will stick those air particles together, and as a result we will be able to observe that temperature is affecting the speed. Now, the second thing about which I talk now is humidity. Humidity, I told you, sound travel faster when humidity rises. So yes, I told you in humid conditions, the particle of the air or the gas in which the sound is traveling or stick to each other through that water drops present in the gas. So that is the second. The third thing which is used to change the speed of sound is the pressure. Change in pressure doesn't affect the speed of sound. If the pressure is high or the pressure is low, it will not affect any of the speed of sound. So keep these three things in mind, that temperature, humidity can change the speed of the sound, but pressure does not affect the uh, speed of sound. With this, we came to the end of this lecture. Thank you very much for your time. Have a nice time.